new chapter, transistor. Okay, now basically your transistors are two type. One is called bipolar junction transistor. Okay, another is your field effect transistor, FET. Transistors. Okay. So what is the difference between these two type of transistor? Okay, we'll take first BJT. So your BJT is short form is BJT. Okay, and the short form of field effect transistor is FETs. Okay, BJTs and FETs. So in bipolar, the name as suggests, okay, it has a two type of charge carriers. Okay, that means you need both majority as well as minority charge carriers. Okay, to explain this operation, or they participate in the operation of BJT. So basically, the difference is that BJT is your current control device. Is your current control device. Okay, we control it by its operation. We control by using current. Okay, and while you need both. Okay, both type of charge carriers. Both type of charge carriers. Okay, majority as well as minority charge carriers. Minority charge carriers. Okay, are required for its operation. While if you take field effect transistor, okay, so these are basically field control devices. And here these are also unipolar transistors. That means only, okay, field controls the flow of majority charge carriers. Flow of majority charge carriers. So here in the channel, okay, in the channel there's one channel. Okay, in the channel only field controls only majority charge carriers. Okay, so they have the difference. This is a they have only one type of charge carriers, unipolar transistor, and here we need both type of charge carriers, electron as well as hole, for to explain its operation. Okay, we'll see how. So now let me discuss BJT in detail. So BJT has 3 layers. Okay, so it has a 3 layer device. So we have 3 layers P. So we have a PNP. So it has a 3 layers. Okay, so it has 3 layers. 3 layers. Okay, consisting 2 junction. Okay, consisting 2 junctions. Okay, so we have 3 layers. Okay, one is called emitter, middle one is called your base, and the right hand side, the third layer is called your collector. Okay, so we can have a either PNP transistor or we can have an NPN transistor. Okay, so one layer is emitter, which will inject the charge carriers. Other is your base, and this is your collector. Now emitter is highly doped. Okay, so emitter region, Okay, emitter region is highly doped compared to comparison to these two regions. It is a highest to get, it has a highest doping. Okay, while your base, okay, base doping is very low. Base doping is base doping is, you can say, lowest, or base doping is very low. Reason I will explain now. Very low. Okay, and your collector region is moderately doped. Okay, moderately doped. Okay, now the thickness of, or area of cross section, okay, this thickness of this base is very less. Okay, so thickness is almost 5 micrometer. Thickness is 5 micrometer. Okay, while the area of cross section of this collector is highest. Okay, so cross section area of collector is large. Okay, large means in compared to other two regions. Now the first region, which is called emitter, okay, we keep its doping very high because this is the emitter of charge carriers. Okay, it will inject the charge carriers. Okay, through this terminal will inject the charge carriers in the transistor. Okay, similarly dope, this base is very small. Okay, if we keep base very high, then it's just like a two diodes, okay, connected back to back. So they will not give any function. Okay, so the fundamental thing, the design of this transistor is the base. Okay, base thickness is very small, so whatever the charge carriers are here, they can easily inject there. Okay, that's why we keep base is very small. Similarly the base doping is very low, so that whenever charge carriers come here, okay, there is a negligible probability to these charge carriers to combine here. Okay, so there should be very low recombination of charge carriers, what we are injecting through the emitter. Okay, that's why we keep its thickness also very small, and doping is also very less. Okay, now p is the collector. Okay, it has to collect all the charge carriers. Okay, it has to charge all the charge carriers, so obviously there will be more power will be generated. Okay, so more current will come, more resistance will be there. So we keep this cross section area high, so that it can easily dissipate heat. Okay, so this is the fundamental reasons. Okay, why their constructions are different. Okay, now we'll see how these operate. Okay, so now as you can see, in transistor we have total two is equivalent to two PN junctions. Okay, so the first junction is called your emitter base junction, and the second is called your collector base junction. Okay, so we have two junctions. Okay, this is called your EB junction, emitter base junction. Okay, and this is your called your collector base junction. So any doubt regarding the construction? Okay, so shall I move further, or you want me to repeat again? Is it fine? So let us move. Now transistor has two junctions. Okay, and so we have EB junction. Okay, we call it also input junction. Okay, and then we have a CB junction, collector base junction. Okay, so now in order to transistor Okay, you want to operate transistor, so we need to give some biasing. Okay, we need to give supply some voltages. Okay, so any junction can be forward bias. Okay, and we can make it a forward bias, we can make it reverse bias. Now here we have two junctions, so there are the four possible way to give the biasing to these junctions. Okay, number one is we can make this junction forward bias. Okay, and we can make it a reverse bias. Okay, when EB junction is forward bias and CB junction is reverse bias, then the operation region, okay, this is called operation region. Then operation region is called your active region. Or region of operation is active. Okay, are you getting what I'm saying? We have two junctions. Okay, so there are possible four way of biasing it. So we can make EB junction forward bias and collector base junction reverse bias. Okay, which is the called FR biasing, and this is the biasing generally we use. Okay, if you want to use transistor as a amplifier. Now second type of biasing is you can make it, this is a forward bias. Okay, and this is also forward bias, both forward bias. When both the junctions are forward bias, then the operation region of transistor will be your saturation region. Okay, now the third biasing is I can make it this as a reverse bias. Okay, and I can make this as a forward bias. Now this type of biasing is just the reverse of first case. Okay, that means now you are trying to make collector as a emitter and emitter as a your collector. Okay, so this is called inverse operation. This is called inverse operation. Inverse operation. Okay, that is not important because we want that our emitter should inject more carriers. Okay, injection should be high. So if you use that is only inverse operation, but this is a rarely used configuration. Okay, and the last configuration is fourth one. Okay, we can make reverse bias and reverse bias. Okay, when both the junctions are reverse biased, okay, in that case your operation region of transistor will be cutoff region. It will be working in a cutoff region. Okay, so you need to understand this thing properly whenever we'll use a transistor. Okay, so you want to find, okay, what is the operation region. They ask in exams also questions that they'll give some circuit, they'll give some biasing, and they'll ask you whether your transistor is in which region is working. It's the operation region is active, saturation, or cutoff. Okay, so that we need to find out. Okay, and how we will find out, we'll see the type of biasing. Okay, if EB junction is forward bias or and then CB junction reverse bias, then it's the active region. Okay, forward biasing, FF biasing, that it is in saturation region. Okay, and if it is a reverse biasing, then it is the cutoff region. Now what is forward bias, reverse bias, all of you know. Okay, a junction is a forward bias or reverse bias, we can easily identify it. If P is connected with the positive of the battery, then the junction is forward bias. Okay, similarly if P is connected to the negative of a battery, then it is reverse bias. Similarly, if N is connected to the negative battery, it is forward bias. If N is connected to the positive of the battery, then it is reverse bias. Okay, so whether it is a PNP transistor or an NPN transistor, by looking the configuration, okay, we can find whether it is a forward bias or reverse bias. Okay, and suppose it is not clearly visible in the circuit, then we can simply find out the voltage. Okay, what is the sign of VCB? Okay, So so this is your VB or VB. Okay. So we can check the sign of VB and VCB. Okay. So for PNP time for PNP transistor, okay. So P and P, your P should be connected with the negative voltage. Okay. So your VCB should be negative for PNP transistor, and VCB should be positive for NPN transistor. If you want to make it reverse bias, okay. If you want to make reverse bias, then PNP transistor P should be connected to minus. In that case, your VCB should be positive, okay. And if it's for reverse bias, and NPN transistor, okay, NPN, we should be connected to positive of the battery. That means voltage drop should be positive, VCB should be positive. That thing we'll discuss when we will understand the operation. But you have to keep in mind, okay, in order to find operation region, you need to understand, okay, that what kind of polarity is there, okay, and sign of this, what is this base on this junction, what is sign of the junction, or voltage drop across this junction, okay, in the sign, okay. Magnitude also important, magnitude and sign you have to understand, okay. So let me now discuss this operation. For example, if I take a PNP transistor, okay. Now transistor has three terminals, okay. As I already discussed, this is a base and this is a collector, okay. So transistor has a three base. So in order to give the biasing, okay, we need to make one terminal as a common terminal, okay. We need to ground one terminal. So based on this, okay, there are three configurations. Transistor can be used in three configuration of transistor, okay. Number is your common base configuration. Common base configuration is also called CB configuration, okay. And number two is your common emitter configuration, or these type of configuration have different characteristics, okay. So common emitter configuration, okay. So we generally use this common emitter configuration. We'll discuss this one also, okay. But throughout this course, I will use mainly common emitter configuration, because that is the configuration where generally we use for amplification, current application and voltage amplification. Okay, so amplification is high in this configuration. So these configurations are generally preferred. Okay, and most of the your exam questions, okay, they are based on common emitter configuration. Once you understand the operation, any configuration can be given. The operation mechanism is same. Okay, only you have to see the signs of the sign, okay, and the values. And the last is your common collector configuration. Common collector configuration is called a CC. Okay, this is called your C configuration. Okay, so there are three configuration where we can use. So first we'll take your common base configuration. Common base configuration. Okay, so in common base configuration, what we'll do, okay, we'll ground this base junction, okay, we'll make it ground, okay, and we'll apply voltage source. So this is your emitter. So let me call this battery as a VEE, okay. So here we have a battery VEE, okay, and here we have a common collector. So let me call this battery as a VCC, okay. Now this is a PNP transistor, so I need to make this as a negative. I need to make it give reverse bias. Okay, so this function should be forward bias, this function should be reverse bias. Okay, if we are going to operate transistor in active region, that is for amplification purpose. Okay, now what is the operation? Okay, so here we have holes, majority charge carriers are holes. Okay, here we have holes. Okay, so when I give forward bias, what will happen? These hole will move. This hole will inject it to the N layer. Okay, N layer. Now in N layer, okay. Now what will happen? Because you are applying plus here, so your holes move this direction. So the current direction will be in this direction. Okay. So this current, okay, which is entering to the ammeter terminal, I call it ammeter current. Okay, now these hole will move. See, this these terminal will inject the holes here, and this hole will move from this side to this side, because this is the very thickness is very small. So most of the holes we are already injecting, they will reach to the collector. Okay, and since collector has there is reverse bias, this collector will collect all the holes. Okay, but in between, because there is the N region, okay, there are some electron also. Okay, doping is low. Okay, but there are majority charge carriers are electron. Okay, so some of this hole will combine this with these electrons. So what will happen? Once these they will combine with the electron, so only some fraction, okay, only a small, very small fraction will be recombined. So most of the electron will reach here, but some electron will be lost here because of recombination. Okay, and that electron need to be supplied from here. So this electron will come here. That means the current direction is always opposite to the flow of electrons, because electrons will move this direction, because electron is getting depleted here. So electron will move from this negative terminal. So current direction will be this direction, and this is called your base current, because this is coming towards the from the base. Okay. Similarly, now here negative is there. Okay. So whatever the holes coming here, okay, this reverse bias. Okay. So this reverse bias, this will collect all the charge carriers here, and they will form a current. That current is called your IC. Okay. That current is called your IC. So basically in transistor, we have three current: IE, IB, IC. IE is the ammeter current. Okay. So IE is ammeter current. Okay. IB is your base current. Okay. And then IC is your collector current. Okay. Now let us understand how these currents are related. Okay. So you know that this side of junction, a current coming IE, okay, to the junction. Okay, and some fraction is getting lost here. Okay, most of the fraction of IE, say called alpha IE. Okay, alpha IE reaches here, and that forms your IC. Okay, so IE current is coming, some fraction of IE, say 0.1% or 10% or 5% is lost in recombination. Remaining 95% or 90%, okay, depending on the transistor. Okay, they form, the charge carrier forms your uh, IC, collector current. Okay, now some of the portion, some of the IB, okay, that will form some fraction 1 minus alpha E, 1 minus alpha of IE, that will form your current IB, isn't it? Okay, so we are making a forward bias junction. So current is flowing and going there. Okay, and some fraction is getting lost here, that is making the current IB. Okay, now just give me 1 minute. Now Yes. In doubt? Confusion? Any confusion?
वो आई जो है होल्स की डायरेक्शन में करंट फ्लो कर रहा है,
Ah, no, I didn't get your question. See, the current direction is always in the direction of holes, na? So I in this direction in movement of there, okay. Now and here we are losing electrons. Electron moving here. Current is opposite to the electron movement. Okay. So IC is the direction of this one. Okay. Now one more thing. Here we have this junction, CB junction also. Okay. And we are making this reverse bias. So we know when we make a reverse bias, then there's a reverse current also. Okay. So when I'm making this as a negative and this is a positive. Okay. So this one current will flow here. Okay, that will be your reverse saturation current, isn't it? So when you have transistor like this, your diode is like this. Okay, and when you make it reverse bias. Okay, so a reverse current flows in the circuit. Okay, so similarly here also one reverse current is flowing in the circuit whenever you apply reverse bias. Okay, and that reverse current is okay going reverse current. Okay, and that reverse current is your going here. Okay, that is called your ICBO, reverse saturation current. This current is flowing like this through diode. Okay, this is called your ICBO's reverse saturation current. So this point is clear. Any confusion? Now I am going to write the current relations. Okay, so this is the current relation in CB configuration. Okay, this is the current relation in common base configuration. Okay, so let me write for now common base. So you from here you can see that your IC is basically equal to what? Your IC is basically equal to alpha IE plus ICBO. Okay, isn't it? Okay. Similarly, you can write the expression for other currents also. Okay. So if I want to write my IB, okay. So IB is what? IB is 1 minus alpha IE minus ICBO. Okay. Now, if I add these two equations, okay, what will I get? I'll get IC plus IB equals to what? What will I get?
IE.
I. Very good. Okay. I. Okay. So, so these are the current relations in your common base configuration, and these three are called fundamental current relations. Fundamental current relations for transistor. For transistor. So that means your IC plus IB combined will give you IE. Is this point clear, everyone? Okay. Now let me define what is alpha. Okay. So this fraction alpha. Okay. So this fraction alpha value. Okay. Fraction alpha. Okay. Which is equal to okay IC minus ICBO divide upon IE. Okay, that is called your current gain. Current gain, okay, of common base configuration. It's the current gain for common base configuration. Okay. Now, this ICBO, okay, because it's a reverse saturation current, okay, it is ICBO is negligible compared to your IC, okay. When you know when there is a forward current is flowing in diode, okay, that is order of milliampere, and whenever there's a reverse current, okay, that is order of what, that is order of only microampere. So we can always neglect this configuration ICB compared to IC, okay. So you approximately, this is the exact relation of alpha, so you can also write your alpha, okay, which is DC current gain, okay, DC current gain of common base configuration, that also you can write as a IC upon IE. Okay, so this is the approximate relation, this is the exact relation. And alpha value, you know, okay, that varies transistor to transistor, but then generally it is almost close to one, only some fraction, okay, 10 to 20%. So let me call it alpha varies from say 0.8 to 0. Say 999 or 95, okay. So that alpha is very small fraction, and it is almost close to your one, okay. Now I know here that my my current equation is IC, okay, plus IB equals to IE, okay. Now put the value of I from this equation. I want to remove this I want to find IC in terms of IB. So what will be IC? IC plus IB will be, okay, I can write IC minus ICBO upon alpha, okay. So I have alpha IC plus alpha IB equal to IC minus ICBO, okay. So from here I can find that IC is alpha is less than 1. So I can write IC, okay, 1 minus alpha equals to alpha IB, okay, and I can send this one there. So I got this ICBO, okay, and from here I can write my IC is equals to alpha upon 1 minus alpha IB plus ICBO. So this is my one more relation for collector current, okay. So if I know the gain of the amplifier, current gain of the amplifier, I know the base current, I know the reverse saturation current, then I can find the collector current of the transistor. So this was your PNP transistor, okay. NPN transistor also same, okay.
Sir, voice is not coming, sir.
सर आपकी आवाज नहीं आ
जा भी नहीं रही है।
Sir. Hello, sir. You're not audible, sir.
Okay, we can send the messages in WhatsApp because he is not listening.
Okay, thank you. So कहाँ से वॉइस गया था?
From starting,
Sir, ये
sir.
starting से
NPN के starting से.
Starting में, okay. So NPN transistor में क्या है? You have 3 layers, okay. Now this region should be the forward bias, so I'm connecting with negative of the battery, and this region should be reverse bias, so I'm connecting N with the positive of battery, okay. Now what will happen? This is the electron here, so now what will come? This will repel this will push the electron inside the transistor, okay. So what will happen? Electron movement is the direction. So obviously current direction will be opposite to the movement of electron. Okay. So your I will come outside this side, IC will go this side. Now when this electron will combine with the holes in this region, okay. So there will be a depletion of holes. So holes needs to come from here. So the IB direction will be towards the base. Okay. So only I was telling that working is same, only the direction of current change when you use NPN transistor. Okay. Of course, this polarities also change when you're using NPN configuration. Okay. Now let us discuss, okay, that characteristics of common base configuration. Okay. So this point is clear. Up to this is clear. Now suppose you want to make a PNP transistor. Okay. So if you want to make a PNP transistor, so you will be say this is my ammeter, this is P, this will be N, and this will be P. So the current direction will be always from P to N. So if in PNP transistor, say this is my ammeter, say this is my ammeter, this is my base, and this is my collector. Okay. So you can identify with the sign. Okay, if sign is going inside, that is your PNP transistor. This symbol, PNP transistor symbol. Okay. Similarly, if you are okay, if it is an NPN transistor, this will be your N. Okay, this will be your P, this will be your N. Okay, so what will happen? They say this is my ammeter, say this is my collector, and this is my base. So direction will be always from P to N. Okay, so towards the ammeter we put a arrow size like this. Okay, here also at ammeter side we are putting arrow. That arrow is inside, that is PNP transistor, arrow is outside. Okay, that is your NPN transistor. Okay, so like you see in NPN transistor the current is going outward. Okay, so here also this current is going outward in NPN transistor. So this is your NPN transistor symbol. Okay, so if you have any confusion, please ask me. Now let us, if you want to understand the operation of a transistor, okay, first of all, why this device is called transistor. Okay, so if you want to understand the working of this transistor, you should understand what are its characteristics. Okay, so what is the characteristics means, what are the relation between voltage and current when we apply forward bias and reverse bias. Okay, how are its input and output characteristics. Okay, so put the heading now, common characteristics of common base configuration. Okay, characteristics of common base configuration. Okay, so here two type of characteristics are important. Number one is output characteristics, which is more important to understand the working of amplifier. Okay, and the second is your input characteristics, which is not that much required, but anyway I will explain this. Okay. So when I'm taking a say transistor, okay, in common base configuration, okay, so say common base configuration means this one. Okay, I need to make this is positive. Okay, so say this is my ammeter. Okay, and say this is my collector, and this is my base, and I'm making the base ground. Okay, so let me call this is a PNP transistor. So PNP transistor, so this is P, N, P transistor. So current will go inside. So I need to supply some voltage here, which I call VCC. So this is P and P. This should be negative. Okay. Similarly, this is your PNP. This should be forward bias. So I am making it forward bias. Okay. So this is my PNP transistor. Of course, there will be some resistances. Okay. So now, what is your input characteristics? Okay. Input current characteristics is so input current here is your IE, and your output current is your IC. Okay. So let me first explain the input characteristics, which is very less time required. Okay, but to make this understand. So input characteristics. So input characteristics is okay, keeping output voltage, keeping or relation between input current and input voltage of okay ammeter base junction okay keeping output voltage constant, okay, is called your input characteristics. Okay, so let me explain this once again. So what I'm trying to say, if you plot graph between input voltage and this VBE, forward for this VBE, okay, you are applying a battery VEE, okay, but there will be some resistance also. And so here the voltage drop, voltage drop will be here, emitter to base. Okay, this voltage drop is VEB. Okay. So similarly here you have a collector, here collector, you base. So voltage loss will be here VCB. Okay. So VCB is called your output voltage. Okay. And VI is called your input current. IC is your output current, and VB, this is the forward voltage here. So if how much voltage is required? This voltage is required to diode to conduct. Okay. So you know from the diode, okay, if you want to make any junction to conduct, okay, you need to apply some cutoff voltage. And for silicon junction, what is the value of this cutoff junction?
0.7.
0.7. Okay. So here also, depending on the whether it is a silicon transistor or germanium transistor,
1.1.
okay, so that value, the VEB, okay, 1.1 is a band gap. Okay, silicon. So you need some here, some voltage need to apply it. Okay, that is called your forward voltage. So now let me draw a forward. So input characteristic means you have an input current. Okay, that is you call IE. Okay, and then you have a input voltage. Okay, or you can say voltage at EB junction. Okay, voltage at EB junction. Okay, that is your VEB. VEB and VB are both same. Generally, instead of writing VEB, we write VBE. Okay, and VB is nothing. This is equal to minus VBE. Okay, and its value is almost like cutoff voltage, like 0.7 for silicon transistor, 0.3 for your germanium transistor, almost equal to, not exactly, but we take it as a 0.7. Okay, now I want to plot the IV characteristic of input junction. Okay, IV relation of input junction. So I have an input current IE. Okay, and I have what I want IE versus VBE. Okay, keeping VCB constant, VCB as constant. Okay, so I am plotting graph, I am applying some voltage, I am applying some VCB. Okay, so I am keeping VCB at output constant, and I am applying current, and I am using the VBE. So once VBE is almost 0.7, after that, okay, after that this current becomes almost increasing. Okay, without any further drop. Okay, you get this exponential increase of current. So this VB value is 0.7. So when we do circuit analysis, that time you should remember, whenever we are in input loop, okay, this VB value is fixed 0.7. Okay, so and this is the VCB value. Say VCB value is say 1 volt. Okay, now if I further increase the VCB, okay, so my this current I will increase. This current I will increase. Say this VCB equals to 2 volts. Okay. So if I further increase VCB, my IE further will increase. Okay. So VCB, so why it's happening? So when you're applying this negative voltage to reverse bias to this output, okay, that output is collecting. Okay, output is collecting this charge carriers. So you can understand this way. It's not exactly like this. When you apply more voltage, the collection is better. So that's why IE increasing. Okay, and there is some variation of VB also. Okay, so you can understand whenever you apply more reverse bias, so applying reverse bias as output junction is equivalent to applying forward bias to input junction. So you're applying more reverse bias, okay, that will affect immediately that your input will become more forward bias. That means if you more forward bias, that means you get increase of current. Okay, so basically what happens when you increase the reverse bias? So what happens because of reverse bias, this output junction, okay, that width of junction increases. Okay, so width of junction increases. That means for your base becomes smaller. Okay, so let me why this current is increasing. Okay, so let me explain. So there is one effect called base width modulation. Base width modulation. Okay, so what happens when you have a junction? Okay, let me call PNP. Okay, PNP junction. Now there is a depletion layer width. Okay, now suppose if I am making this junction more and more reverse bias, PNP, okay, more and more reverse bias, then what will happen? This junction layer width will increase, isn't it? It will increase or decrease when I have a reverse bias. So when we're increasing the reverse bias, this layer will increase. So automatically this base width will decrease. Okay, effective base width will decrease. Okay, so slightly. Okay, so this once this base decreasing, that means now there is a less recombination IB, isn't it? So there is a less recombination. That means now you will be lost, less injected carrier will be lost. So most of them will reach here. So that may be one reason that I is increasing. Okay, and another reason I told you. Okay, because when you are increasing the reverse bias or output, that is equivalent to increasing the forward bias to input. Okay, so you can write this effect is called early effect. This relation is called early effect. Okay, so you can write what is the early effect. Okay, so as reverse bias increases, as reverse bias increases, okay, as reverse bias increases, the space charge width, okay, that also increases. Okay, between collector and base, between collector and base increases. Okay, so when this is increasing, so what is happening? Okay, collector and base increases. Okay, which decreases the base width. Okay, as a concave, which as a result, okay, decreases the base width. Okay, now once base width decreases, okay, so base width has a two consequences. Okay, so it has a two consequences. If base width decreases, okay, what happens? There is a less chance of recombination. there is less chance of recombination. भी एक तो बेस कम हो गया तो recombination तो कम हो ही जाएगा. Okay, and the second point here, which is the more important, okay, what happens that your minority charge carrier gradient increases. Minority charge carrier gradient increases, okay, which causes okay more diffusion, okay. So as you increase the reverse bias, base width decreases, that result in decrease of base width. This result in less recombination. As well as second point is because the minority charge gradient increases towards this region, okay, so this which cause more diffusion, that I told in the beginning. Applying reverse bias at the collector base junction is equivalent to slightly increase forward bias to your input junction, okay. So only in input characteristics you need to remember one thing, that your VB value is 0.7 for silicon and 0.3, okay. That much is only important for us in when we're doing the problems, okay. Now the next thing is which is more important, that is the output characteristics, okay. Let me discuss that in detail. So next is your output characteristics, okay. Now output characteristics means your output voltage, output current is, which is output current,
VCB.
output current
IC.
output current is your IC, okay, and output voltage is your VCB. Output voltage is your VCB, okay. So your output characteristics is basically a relation between IC versus VCB, okay, keeping what input current I in this particular question, particular common misconception, input current is IE, keeping IE constant, okay. So this is your input current, okay. So I'm writing an input current. So this characteristics is called your output characteristics, okay. Now let me draw the output characteristics. So output characteristics means you have IC value, okay, and then you have a VCB value, okay. So when you increase the VCB, okay, so for example, if my IC comes because of IE, okay, if there is a no IE, then what is the value of IC? Suppose IE is 0, then IC value will be automatically 0 if there is no IE, okay. And IE becomes 0 when? How to make IE 0? How can we make IE 0?
Reverse bias.
Reverse bias.
Okay, so if suppose if we don't apply any voltage to forward bias junction, okay, forward bias junction also needs 0.7 volt, isn't it? So suppose if you're not applying at 0.7 voltage, you're not getting any IE, so IE automatically becomes 0. So not applying voltage also is a kind of reverse bias, isn't it? If you're not applying any forward voltage, you're applying 0 voltage to input, that is also reverse bias. because it will become forward only when you apply 0.7, because VB is 0.7. Until you don't apply 0.7, you don't get any current, forward current. Okay, so either you are applying reverse bias to input, okay, or you're applying zero bias. That both is called your reverse bias. Okay, so when there's no, you don't applying when your IE is 0. Okay, so when IE is 0, that time IC should be 0, but IC is not 0. Why? But IC, so when you're applying here,
reverse saturation.
Some reverse saturation current.
very good, because your IC is two component. Okay, one is the reverse. So even if you have IE 0, you have made your input EB junction reverse bias IE 0, but then also you got some current here IC. Okay, here this IC, here this particular question IC is equals to ICBO, reverse saturation currents. Okay, now this here VCB is positive. Okay, VCB is positive means
Output
if,
voltage.
okay, so I am drawing this for NPN transistor. Okay, this for NPN transistor. So NPN transistor, say this is my and common base configuration. Okay, so this is my NPN. Okay, say NPN transistor. So current will be always P2, current will be like this. Okay, and this is my collector. So current is going outside, current coming here, and current coming here, IB coming here. Okay, so this is my EB junction. So EB junction is forward bias. Okay, so this will be your what VEB. Okay, but I plotted VB. Okay, because both the same and sign is different. So here you have a base, and this is your collector. So here you have VCB, and now to make VCB, I need to apply reverse bias, so this should be connected to plus. Okay, so my this VCC is positive. So this positive, that means now this voltage drop is positive. VCB is positive, isn't it? This drop is positive here. Okay, there will be some resistance also, but for the moment, if any loop, if you apply any current in a loop, okay, so this drop will be positive. So VCB is positive. That means this is a reverse bias, and this here IE is 0. IE is 0. That means this is also reverse bias. So reverse bias. Okay. So then the operation region is
Cutoff.
cutoff region. Very good. So when both have reverse bias. Okay, because we are not giving any current IE 0. So this is called this region where your forward, this region is called your cutoff region. Cutoff region. Okay. So the cutoff region means there is a minimum current, okay, to output. Okay, that's why it's called like a switch off. Okay, switch off means no current. Transistor is working as a switch off. Okay, now similarly, now suppose I'm making the forward bias as a positive. So if I make positive, what will happen? Or obviously some current will flow. Okay, say this is 1 milliampere, 1 milliamp so IC na. So say IC, this is IC, say in milliampere. Say this is 1, say this is 2, somewhat less than 2, this is 3, this is the 4. Okay, now I know the IC will be almost equal to IE. Okay, so suppose if I make a IE equals to, if I fix IE equals to 1 milliampere. Okay, so my IC, this is IC value, will be slightly less than this is IC value. Na? This IE is fixed, and IC value will be slightly less than this 1 milliampere, so 0.9 milliampere. Okay, similarly, if I put IE equals to 2 milliampere, so this is the IC value. So IC for IE equal to 2 milliampere. Okay, so IC values are slightly less than your IE. So this is my IE equals to 3 milliampere. Okay, and then I have IE equals to 4 milliampere. Okay, so here I have, this is a cutoff region. Okay, and in this region I am making that is forward bias. My input is forward bias. Input is forward bias, and the output is reverse bias. So I am getting almost constant current IC here. Okay. Now suppose I am trying to make my output as a forward bias. If I make VCB negative, if I go this direction, VCB negative, so what will happen? This become forward bias. If I make negative VCB negative, so this become forward bias. Okay. So forward bias means now whatever current is coming, that will current will it will not collect. Okay. So that will have, so what happen if you apply in this output in forward bias, so slowly this current will become zero. Okay. And in this region your VCB is forward bias, your input is already forward bias because this current is coming, so the input forward bias. Now slowly you're increasing the voltage in opposite direction. Okay, that you are making this is also forward bias, so automatically at some voltage value you'll get zero current. Okay, but in this region your output also forward bias, your input also forward bias, both are forward bias. So this region is called saturation region. Okay, so both are forward biased, so that means this is called saturation region. Now please do not confuse that this is saturation. This is a constant IC value. Okay, depending on IE what you apply, you're getting. Okay, this is not saturation. This is not saturation. Okay, saturation region means when your switch is like on, resistance is very low. Okay, so what will happen? This part has a very high resistance, but this part has a very low resistance. Okay, like if I call you that input resistance, I draw the input characteristics. If I calculate the resistance, that will come in ohms. Okay, now similarly if I try to calculate the resistance here, okay, so this resistance is very high. Okay, in this part resistance is low, you are increasing the decreasing the voltage, your current is increasing. Okay, so this part has a IV characteristic like Ohm's law. This has a very slope is less, and this is a very high slope. Okay, or zero slope. So zero slope means what? If some slope is zero, so if I want to calculate, say I want to calculate my resistance R of output in common base configuration, that will be what? Delta VCB upon delta IC, or VCB upon ICB. Okay, and now slope of this graph. What is slope of this graph? Slope is what? This slope is what? Delta IC upon delta VCB, and that is 0. Okay, so ROB will be almost equal to infinite, isn't it? Are you getting my point? Resistance is defined how? Resistance is defined by VCB upon V upon I is resistance. Okay, but this graph has a, we have drawn I versus V. So IV versus has a slope IC versus VCB is 0. If I put here ICB but from VCB 0, this will come infinite. That means this region has a very high resistance. Okay, or you can understand this is like this. Suppose you have IE and V like this. Similarly, if I plot this curve as a V up, so this is your IV. Suppose I plot like this curve like this, VI. Okay, then this graph will be like this. Okay, this plot. So this is a slope 90, 10 90, 10 90 is infinite, 10 90 and 10 90 is infinite. V upon I, the slope of this graph is infinite. Okay, slope of the graph is infinite, this resistance is infinite. So this output resistance, this is very high resistance. Okay, so order of say 500 mega ohm, say this order of 500 kilo ohm, 500 kilo ohm. Okay, kilo ohm or 500 kilo ohm or 1 mega ohm. Okay, 1 mega ohm. So this is very high resistance. Okay, now while we see the input resistance, when we plotted input curve, that resistance you can write there, the resistance is order of 25 ohms, 20 ohms. Okay, so why this transistor is called transistor? Okay, transistor is called transistor because the meaning of transistor is transfer of resistance. Okay, so transistor means call your transfer of resistance. Now transfer of resistance means you have an input junction has a low resistance input junction, okay, and you have output junction, okay, or input characteristics. Okay, you have a low resistance, and then you have here you have a high resistance. Okay, so one side has a low resistance, other side has a high resistance, but the current values are same. Okay, so what gets amplified? Resistance is change, current is same. One side is IE current, other side is IC. IE and IC almost same. Okay, so current is fixed, and resistance is increased. So what will increase? So what quantity get amplified? Which quantity will get amplified?
Voltage.
Output voltage.
Very good. Okay, V equal to IR. So I is same, R is increasing. So that's why this times is common base on this configuration. Okay, and common base or common emitter, any configuration. Okay, the value always increases. Only here the resistance very high. Other configuration resistance maybe that not be increasing that much. Okay, so that's why you get voltage amplification. Okay, current is same, voltage increasing, so you get power amplification. Okay, so that's the reason that is called transistor, because it is a transfer of resistance which gives you the amplification. Okay, so this was your common base characteristics. Okay, so that is also important, but the most important is for us is common ammeter configuration. Okay, so now let me discuss this common ammeter configuration. Okay, 5 minutes, then we'll solve the problems. Now onwards I will be only using this NPN transistor. Okay, for most of the part of this transistor part. Okay, some problem we'll do with PNP also. Once we understand the NPN transistor working, then we'll do this understanding of this. We'll do some problem on PNP also. Just give me 1 minute. This NPN transistor. See, this is my ammeter. See, this is my base. So this is my collector. Okay, now what I'm doing, I am making collector as a reverse bias. Okay, so I'm applying some voltage here. So this voltage NPN, I have to make reverse bias. So say this is a VCC. Okay, and here I'm applying to base. So say call this battery should be forward bias. So this battery should call PPB. Okay. Now this is your common emitter configuration, NPN transistor. So NPN transistor, what current will be from P to N. So current will be this side, IE. Okay, IC will come inside, IB also come inside. This is a common emitter configuration.
Why you make this diagram इस टाइप मतलब perpendicularly.
You can make like this, no issue. Okay, because I want to make ammeter common ना, इसको ground करना है ना मुझे.
Okay.
Okay, so you can make like this also. Okay. Say this is NPN transistor. This is grounded. Okay, this is your VCC. VCC. Okay, NPN. So current will be I will be outward. Okay. So NPN transistor, and this is say here is you have plus. So this will be your say VB. Okay. Now in the common ammeter configuration, okay, your input
माइक
current
से
is
आवाज
what?
आ रही है.
Mic से
Yes sir.
okay. I hope now it is correct. Okay, corrected. So now in common ammeter configuration, your input current is what? Your IB, isn't it? And your output current is what? Output current is still IC. Output current same IC. Output current. Input current is now IB. Okay, and input voltage here again BB. Okay, base is common, so the voltage of base compared to ammeter. Okay, earlier it was VB, but I wrote VB because that was both same. Okay, only signs change. So now input voltage is VB, input current is IB, output current is ICE. Okay, and output voltage, what is the output voltage here? What are the output voltage means? The voltage at output terminals. Input voltage means the voltage at input terminal. Okay, so input terminal is base ammeter, so the input voltage is VB. Output terminals are now C and E.
VCE.
VCE. So that will be your VCE. So now this is your VCE. So now this output voltage will be your VCE in common ammeter configuration. Okay, always remember this is output voltage, voltage across output terminals, voltage across input terminals is input current and output current. Okay, now before we discuss the characteristics of this common ammeter configuration, let me write the current relations. Okay, so we have to write the current relations for common ammeter configuration. Okay, so
Sir, voice gone.
just 1 minute.
Audio.
I know. Just 1 minute. Okay. So now this equation, this is same equation what we derived here. Okay, and I is equals to IC plus IB put the value here. IC, okay, alpha. So this become alpha IC plus alpha IB, okay, plus ICBO, okay. Now, if I want to write IC, okay, so IC will be what? If I send this one, so 1 minus alpha, okay, alpha IB plus ICBO, okay. So this actually I already derived, okay. So IC is the thing, IC is just my alpha upon 1 minus alpha IB, okay, and ICBO, okay. So this alpha upon 1 minus alpha, this is nothing, this is called beta, beta IB plus ICBO, okay. So this is the current relation for your common emitter configuration, okay. Where beta is current gain in common emitter configuration, beta is your current gain in common emitter configuration, okay. And what is the value of beta? Okay, so beta is your alpha upon 1 minus alpha, okay. So suppose your alpha is 0. Say 1, okay. So what will be 1 minus alpha? Okay, 0.9, okay. So if you solve this, how much value should come? Alpha upon 1 minus alpha.
1/9.
1/9. Okay, no, it's not correct.
Sir, 1 minus alpha ICBO के नीचे भी तो था.
Yes. Okay. यहाँ पे था क्या? हाँ, 1 minus alpha. Okay, 1 minus alpha. Okay.
Beta plus 1 relation.
So you can write this is a ICEO. ICEO upon 1 minus alpha. You can write ICEO. Okay, and beta is 1 minus alpha. Just let me correct one thing about what I'm writing wrong. It should come alpha upon 1 minus alpha. Na? Alpha upon 1 minus alpha. This correct. Beta. Okay. Just give me 1 minute. So beta IB plus ICO. Now is it correct now? Is there any mistake now? Okay. So ICO is what? This time I'm writing ICO. ICO is reverse saturation current. Reverse saturation current. Okay. In common emitter configuration. Common emitter configuration. Okay. So now this, how to write this beta value should be very high. Okay, let me, alpha is actually your 0.9. okay, so I'm what I'm writing, alpha is your very high, alpha is a fraction. Okay, how much is fraction is going to IC? Okay, suppose your alpha is 0.9 and this is your 1.11 minus 0.9. okay, so almost how much is coming? 0.9 divided by how much? 0.1. 0.1 is coming 9 only. Okay, and if I write like this 99, okay, so if you write 99% is coming, then this will become 0.01. okay, so 0.01 this become your 100. okay, 100. So generally what I'm trying to say is the beta value gain is very high. Okay, so gain is, this is called beta. Okay, beta is your current gain. Okay, current gain whose value is very high. Okay, so that's which you can take value between 50 to 500. Okay, depending on how transistor is made. Okay, so some question it will be given 50, some question it will be given 100, some question it will be given 200, 300. So you can take a range of beta value. Okay, beta range value is very high means what? Beta value is very high means your and this alpha. Okay, alpha the fraction, this the 1 minus alpha is very high, almost close to 1. Okay, when alpha is very close to 1, that means all the current is IE is getting converted into output current IC. Okay, so generally this beta value is very high. Like I told you, alpha value is your 0.82. Okay, 0.99. Similarly, you are here. The beta value is very high. Okay, 52, 100, 50. So that will be given in the problem. Okay. Any confusion here? Any confusion here? Okay. So if no confusion, let me now discuss that your characteristics, input and output characteristics. Okay. So input characteristics are like same. You have IB and you have here VB. Okay. So that is your input characteristics. Okay. So your VB will be almost 0.7 VB. Okay. And this time, if you increase the VCE, keeping VCE constant, okay. So input characteristics means your IB versus VBE, keeping VCE constant, okay. And this time, if you increase the VCE say this is 5 volts, okay. Why VC equals to say 1 volt, okay. This is for 2 volts and this is for 3 volt, okay. So here is same relation. When you increase the VCE, your IE also increases, okay, because your VCE is equal nothing. VC is equal to your VCB plus VBE, okay. Suppose if I draw a transistor, okay, common emitter, okay, and this is collector, this is your base, okay. This voltage is called VCE. This is equal to your VCB plus VBE, okay. So VB is always constant, okay. VB is almost constant. VC once you VB is 0.7. So if you increase the VCE, so what will that will VCB increases, okay. VCB increases, then what happens? If VCB increases, then what happens?
VCE increases.
VCB increase, then just give me. So VC 2, 3, 5. Okay. So VCE, VCB, VC increases and VCB increases. Okay. So your IB is also increasing. Okay. That is your so you can say VC increasing, your VB also increasing. Okay. VC increasing. VB is 0.7, but slightly varies. Na? Slight variation is there. So when you're increasing this one VCE, okay, there is slight variation in this one. Okay, so what happens? Your this forward bias voltage, for you increasing here, forward bias voltage increases here, so you get increases IB also. Okay. Now, so this is input characteristics, not important. Okay, for us most important is your output characteristics. Okay, so output characteristics. Now this is the most important graph of this transistor. Okay, you need to understand this graph. Okay, so with this only we'll do all the problems will be solved. Okay, so please keep focus here. So you have IC here, okay, here VCE, and I'm keeping input current as a constant. Okay, so when input current is 0, okay, IB is 0, IB is 0, IB will be 0 when my input voltage is input junction is reverse bias or 0 bias. Okay, so IB will be 0. This is already reverse bias. VC positive, that is already reverse bias. NPN transistor. This NPN transistor. This characteristics of NPN transistor. This region is called again cutoff region. What we have seen earlier. This is called cutoff region. Cutoff region. Okay. Now if I increase the IB, so this will be say 1 milliampere, IC will be in milliampere, 2 milliampere, 3 milliampere, 4 milliampere. This is my IC value. Okay. Now suppose I'm increasing the VCE. Okay, I'm increasing now IB, keeping IB constant. I'm increasing the VCE. So VCE say beta value for transistor is 100. Okay. So now suppose if I get IB equal to 10 microampere, if I get IB equal to 10 microampere, so now my IC will be how much? If IB is 10 microampere, so my IC is beta IB, isn't it? So beta is 100, 10 microampere into 100, 1000 microampere, that is equal to 1 milliampere. If now I increase IB 20 microampere, so my IC will be what? IC will be 2 milliampere. Similarly, if I increase IB up to 30, IB equals to 30 microampere. Okay, then my IC will be 3 milliampere. Okay, and this region, okay, this region where you are getting almost constant slope, high rest region, this region is called your active region. This region is called your active region. Okay, this is your cutoff region, and this region already we discussed. This region where you are, this region means what? Region close to VC is 0. This region is called your saturation region. Saturation region. Okay. Now, what do you mean by saturation region? Okay. Now, saturation region means, saturation means what? Saturation means what? Saturation in common emitter. Saturation region means, okay, your VCE is almost 0. When your VCE is almost 0, okay, that time the transistor will work in a saturation region. Okay. Now, what do you mean by VC 0? I told saturation region means both junctions should be forward bias. Now I'm saying VC is 0. Okay. So what is the meaning of that one? Because we can only find the definition is what? Forward bias, current based junction forward bias, input junction forward bias. Okay. Now if I take, I told you VCE equals to VCB plus VBE. Okay. Now once VCE is 0, my VCB become minus VBE. Okay, in NPN transistor, and this become minus 0.7. So VCB become negative. That means now junction is what? Forward bias. Are you getting my point?
Yes, sir.
VCB should be always positive for reverse bias in NPN transistor. N should be connected when you apply N. VCB should be positive. Okay, we have to always see input junction not like this VC junction. We have to always see junction, which junction? Emitter base and your base and collector junction. That are our two main junction. Okay, so emitter base, this configuration is different. Even though we are applying VC here, but we have to always see whether my input junction, that is emitter junction, is whether reverse bias or forward bias, whether my collector junction is reverse bias or forward bias. Okay, so that we have to always check. Okay, so here now you have to check. So VCB almost become forward bias. That means now this region is saturation region. So whenever you have VC 0 coming close to 0, you always doubt that whether my region is active region or saturation region. Okay, now how to confirm that my operation region is active and saturation? That we'll check. Okay, that we will check. Okay, further. Okay, just give me 1 minute. विचार है so I'm stopping here. Okay, I don't want to continue so many things. Okay, so we'll discuss tomorrow. We'll do some problems and we'll again understand how to find out whether my transistor is working in operation active region, saturation region, or cutoff region. Okay, how to exactly find that one. So we'll do tomorrow. Okay, so आज की क्लास के लिए कोई क्वेश्चन तो पूछिए. If in doubt. Okay, so if there's no doubt, okay, so I'm stopping here.
Thank you, sir.